All right, so let's look at the concept of limiting reagents. And now, limiting reagents can sometimes be a bit of a daunting topic, but the basic idea is that your balanced chemical equation, as you always write it, gives you the ideal stoichiometric relationship. So it says if you write something like 3A plus 2B gives 2AB, that tells you 3 mole of A will react with 2 mole of B to form 2 mole of AB, right? That's what our chemical equation tells us. But the question comes in, what happens if we only have 1 mole of A, right? And we still have 2 mole of B. What happens then? Is all of the moles of A going to be used in the reaction? Are all of the moles of B going to be used in the reaction? What does your intuition tell you? Is there maybe one of these reagents going to be used up completely? Or is one of them going to remain in excess, meaning there's too much of it, right? And that's exactly the point, is one of them is limiting. It's limiting the reaction, meaning that you can clearly see here that there is not enough of A to react with all of B, because we need at least 3 moles of A to react with 2 mole of B. That's what our chemical reaction tells us, right? That's what a chemical reaction does. Those stoichiometric coefficients tells us information about how the reaction needs to work, how it must function. So if I need 3 mole of A to react fully with 2 mole of B, but what's the problem? I only have 1 mole of A. So that means that we have too little of A. So that means A is limiting my reaction. And what is it limiting? It is limiting the amount of AB that can form. So meaning that there is going to be less AB that forms than what you would expect, or meaning, not expect, but meaning they would form less AB than if there were 3 mole of A that were reacting. And that's basically what a limiting reagent does. It dictates how much of a reagent will react and how much product will form. So this is what this section is about. If one reactant is present in limited supply, so meaning like A, it will dictate how much of B will react, and then hence how much of B will remain over in excess, how much extra of it is there, and how much of AB will be able to form. All right, because it will not form this so-called ideal amount, it will form a different amount because we have a different ratio as we have here. All right, cool. So I have something here about cakes and eggs and whatnot. Maybe if that helps you understand a bit better, I hope it does. If it does not necessarily, then if you want to keep to the pure chemical explanation, then that's also good. All right, so calculating limiting reagents. As a reminder, with stoichiometric calculation, you always need to go to number of moles first. So that's what we're going to compare. Notice how I started the conversation with moles. I didn't speak anything about mass. I went to number of moles. Then thereafter, once we've gotten the moles, then we can go to expected masses. And then from the limiting reagent, we can then determine product masses or maximum masses that we can obtain. Your textbook provides a nice summary here of limiting reagent. Of course, sorry, I just skipped over these points, but it just says you can calculate excess reagent masses, and it says summarize information in an amounts table. But anyway, we'll look at that in the example just below. Your textbook provides a very nice problem-solving tip here. It's just how to look at all the numbers, but that's essentially what we'll do in the example below. All right, so at the hope that this video doesn't become too long, let's look at our example. So it says, methanol, which can be used as a fuel in racing cars and in fuel cells, can be made by the reaction of carbon monoxide and hydrogen, so CO and plus H2. And there's some balancing here, gives that. Suppose that we have 356 grams of carbon monoxide and 65 grams of H2 that are mixed and allowed to react. What mass of methanol can be produced? All right, so we're given two masses of our reagents, and we're told they're mixed together. And now we're asked, what is the mass of the product, right? Methanol is the product. So what would your starting point be here? You're given the two reagent masses, and you're given the chemical equation. So the question here is either one of them in excess? In other words, is either one of them limiting? In other words, limiting the reaction to proceed and hence dictating the amount of methanol that can form. All right. So that is relevant for any reaction where there are two or more reactants, and then you'll have any amount of masses, because then there can be a limiting reactant. So our starting point here for A, a good logical starting point would be, we're given mass, so it would be to calculate the number of moles, because then we can see if any of these two would be limiting in that sense. All right. So let's start by calculating the number of moles. So number of moles of carbon monoxide and number of moles of hydrogen. Number of mole of carbon monoxide. So technically, so you remember that number of moles is mass divided by molar mass. But our dimensional analysis method, we have here 356 gram carbon monoxide, and we have here 65.0 gram hydrogen. All right, this we multiply, there would be 1 mole carbon monoxide per 28.01 gram carbon monoxide. So it's the same as dividing by the molar mass. And then you get 12.7 and some numbers mole carbon monoxide. For the hydrogen, there's 1 mole hydrogen for every 2.016 gram hydrogen. This gives us 32.2 mole hydrogen. Okay, so now that we have the number of mole, there's a couple of ways that you can determine the limiting reagent. But let's remind ourselves on how to determine, let's remind ourselves of a couple of things first. We have the chemical reaction. So that gives us the ratio. So we know that there's 1, so we need, it's 1 mole CO reacts with 2 mole H2, which forms, just move this up, gives 1 mole of methanol. All right. You can almost already see it, but all right. So let's leave it up there. So now the question is, how can we find a method of testing which one of these reagents might be in excess and which one more limiting? And I typically just say test for one of them. So meaning, look at one of them and ask yourself, how much would this one need to react with the other one? So let's say, I just want to make this a bit smaller. If you say, for example, so we know 1 mole of carbon monoxide reacts with 2 mole of hydrogen, right? That's just from the equation above there. We currently have a situation where we have 12.7 mole carbon monoxide. Theoretically, with how many moles hydrogen would that react? Would that react? Well, would that react? Remember, that's your X you typically want to solve with. And if you quickly check that, then you should get here. So if you do your cross multiplication and solve with that, you're going to get an X value that is roughly 25.4. Yeah, 25.4 and some numbers, mole H2. Right, this is just a check that I'm doing here. Right, because there goes a 2 goes to that side, 1 goes to that side. And that gives you that you need, for 12.7 mole CO, you need only 25.4 mole hydrogen. So that's how much hydrogen we need to react with 12.7 mole CO. How much hydrogen do we have? Did you calculate that? Yes, you calculated that. That's how much you have. We have 32.2 mole. Do you agree that 32.2 mole hydrogen is more than 25.4 mole hydrogen? Indeed it is, right? So that means from this calculation that we did here, our hydrogen is in excess. And by extension, therefore, CO is our limiting reagent. Limiting reagent. Okay, that's how you check. You could also have done it the opposite way around, right? You could have said 1 mole CO reacts with 2 mole hydrogen. How many moles of CO? And we have 32.2 mole hydrogen. This would have given a value of X divided by 2 there, so that's 16.1-ish mole CO needed. The question is, if we need 16.1 mole CO to react with 32.2 mole of hydrogen, how much CO do we have? We only have 12.7. Do you notice that we don't have enough CO to react with all of the hydrogen that we have? All right, so we still get to the same conclusion. Okay, your textbook provides another solution to this problem. They first calculate the mass of the product that could be produced based on each reactant, and then they go with the one that is the smaller mass. That's also perfectly fine. I just like this method. So we've now determined that carbon monoxide is our limiting reagent. Okay, so hence, now that we know what is our limiting reagent, what does that tell us? What can we do with that information? Once we have our limiting reagent, it means it dictates the mass of the product. Mass of CH3CO is dependent on number of moles of CO. So that is why it's important, because our limiting reagent dictates how much of our product can form. All right. So the next important part is we need to now look at what is the mole ratio between our limiting reagent and our product. And we see that is 1 to 1. So 1 mole of CO produces 1 mole of CH3CO. And so that means the number of moles of CH3, oops, not CO, OH. Ooh, goodness. You see, it's been a very long day for me. OH would be the same as our CO, which is also 12.7 and a bunch of numbers mole CH3OH. You know what I hate about videos is I can't get any confirmation whether or not you're following. So just move on though. But anyway, the point is we determined that CO is our limiting reagent. That means whatever the number of moles is of our limiting reagent, that will dictate how many moles of anything else that is a product that will form. Okay. In this case, it is a 1 to 1. So meaning it immediately gives us the number of moles. If this was a 2 or a 3, we would have had to do some calculation to determine the number of moles that form. But in this case, it's 1 to 1, so we can just immediately write it. Okay. So now we know the number of mole of methanol that form. So from that, we can just determine the mass of methanol. Because once you have the number of mole, you can always just get the mass using the molar mass. So you can use the 12.7. So it's mole CH3OH. And that's multiplied with, of course, the molar mass. So that's 32.04 grams CH3OH per 1 mole CH3OH. So multiply there, and that will give you a mass of 407. There's some numbers there. Gram CH3OH. CH3OH. Okay. Technically this is our final answer, so we can round it to 3 significant figures. Yes, 3 significant figures. So I can actually just round it there. 407 gram methanol. All right. And that is the end of A. So the amount of carbon monoxide available produces less product than the amount of H2 available, right? Why? Because CO is the limiting reactant. So the maximum mass of methanol that can be produced is dictated by the CO molar or number of moles, because it's a limiting reagent. Okay, so there you can see it. All right, so I hope you followed it nicely. You can check it. You can check what your textbook does. They have just a slightly different way of doing it. It comes down to the same thing. Okay, let's make a nice little thing here for ourselves to do the B part. All right, B asks, what mass of H2 remains when all the CO, or what mass of excess reactant remains after the limiting reactant has been consumed? In other words, what mass of H2 remains after the limiting reactant has been consumed? So what mass of H2 remains once CO has been consumed? So now we just need to first determine what mass of H2 is in excess, right? That's actually what we're trying to determine. So first we must find the mass of H2 required to react with our limiting reagent. So the point here would be, we know already what is the number of mole of H2 that is required to react with the limiting reagent. We've determined that already. So we can just immediately calculate the mass H2 required. You can call it required if you would like, required, because that then would be number of moles multiplied by the molar mass. Yeah, number of moles multiplied. Sometimes I just actually have to check myself. So it would be this 25.4, 25.4, and some numbers, gram, not gram, mole H2, multiplied by the molar mass, which is 2.016 gram H2 per 1 mole H2. That gives us a value of, we need 51.25 gram H2. Maybe let's make a note here that it is so much H2 required. All right. So if we require this much H2, how much H2 did we start with? We started with 65 gram. Okay. So this means our mass of H2 left, left is equal to 65.0 gram minus 51.25 gram. That's going to give you 13.8 gram. Right, left. H2 left. All right. And that should be, that's typical of these examples. So you have one reagent in excess, which is the hydrogen. You have one reagent which is limiting, the CO. It's completely used up. And then you have a product that is formed, but it's dependent on the amount of CO that is present. So I quickly want to draw something up here, which we call an amounts table, right? So typically how you do that is you write the chemical equation here. So CO gas plus 2 hydrogen gas gives CH3OH. That's a liquid. All right, let's draw it like that. And we want to look at the initial number of mole. We want to look at the change. So instead of using that, I'm going to use change, number of mole. Some of you might recognize this, start to recognize this, and then let's call it not equilibrium, but let's call it end. End, all right? The end mole. Okay. So for each of these, what is the amounts that we had? Initially for CO, we had 12.71, right? And for hydrogen, we had 32.2. Actually, I just left these as numbers, right? So let's just left them as that. And how much methanol did we have? We didn't have any methanol. Then what was the change? What happened to all the CO? So CO was our limiting reagent. So that means all of the CO was used up. It means all of the CO must have been used up. And how much hydrogen was used up? twice as much as the CO, because CO is the limiting reagent. It dictates what are the mole amounts that are being used. That's the important thing about the limiting reagent. And again here, for the methanol, the limiting reagent dictates the amount depending on the stoichiometric numbers. Okay, so at the end, how much CO do we have left? Nothing, because it's the limiting reagent. So a limiting reagent should always end up at 0. Your other reagents, they will end up at some number. So this ends up being 6.82. And your product, you will see, has gained some number of moles. So 12.7. And that's what you can summarize in your mind as well. So your limiting reagent goes to 0, because that's what a limiting reagent does. It's completely consumed in the reaction. The other reagent, there's too much of it, so it's in excess, right? That's what we call excess. So there remains a bit of it left after the reaction. And your product, it started out here, in this case, as 0. Sometimes there could be some product, but it started out at 0, and it was dictated by the amount of the limiting reagent. Notice how the hydrogen did not dictate anything about the methanol. It was the CO, it was the limiting reagent that dictated everything about the methanol. Okay, so this is a simple example trying to describe the fundamentals of what the more difficult examples can do. All right, I hope this was broad enough and well enough explained. Thank you for watching.